All right, here's our example for potential energy curves. So we have a 2 kilogram particle moves along an x-axis in one-dimensional motion while a conservative force along the axis acts on it. The potential energy associated with the force is plotted in figure 8-10a, which is shown here. The reason I'm covering up something is because we have to find that first. So I'm covering it up with my little screen, and then we'll make everything bigger so it's easier to see. That is, if the particle was replaced at any points between x equals 0 and x equals 7 meters, it would have the plotted value of U, which is the potential energy. At x equals 6.5 meters, the particle has a velocity of -4 meters per second I hat. A, from the figure, determine the particle's speed at x1 equals 4.5 meters, and then B, where is the particle's turning point located, and C, evaluate the force acting on the particle when it is in the region 1.9 meters to 4 meters. So with that information that it tells us at the very end here, it says at x equals 6.5 meters, the particle has a velocity of -4 meters per second I hat. Now, what they're giving us here is they're giving us information in order to find the total mechanical energy. Because what we can see here is that at this 6.5 meters, which is right here, we have all kinetic energy, right? The potential energy is actually going down to 0 here, and maybe even going negative, because potential energy can be negative here, but really we're just going to say, okay, it's probably just 0 potential energy at this 6.5 meters, which means that all of our energy is in kinetic. So because of that, we can find the total energy. So for A, well, we're determining the particle speed. So the first thing we're going to do is find the total mechanical energy. So at that 6.5 meters, E total is equal to kinetic energy, okay? So our total energy is going to be 1/2 mv squared. Now they tell us that the particle's mass is 2 kilograms, and then at 6.5 meters, the velocity is a -4 meters per second. So what we get here is total energy is equal to 1/2 times 2 kilograms times a negative, but we're squaring that, so we can really just use 4 meters per second, and then we're going to square that. So 1/2 times 2 is just 1, 4 squared is 16, so our total energy is going to be 16 joules, which was already drawn on the figure. So that's why I covered that up right there, is we get this right here from this last sentence, that information in that last sentence. So usually in these problems, you are going to get information in where you can find the total energy. They usually don't just give you the total energy. So now that we found that, we can now find letter A, which is the particle's speed at 4.5 meters. So I'm going to make this a little bit bigger so it's easier to see. And I'm going to move myself down here. All right, so now that we found the total energy, for part A, we want to find V at x equals 4.5 meters. So 4.5 meters is right here. Okay, so if we're looking at this graph right here, we can see that at 4.5 meters, our potential energy is 7 joules. So that means that our kinetic energy will be the total energy minus the potential energy at that point. So kinetic energy is equal to 16 joules minus 7 joules, which is our potential energy at 4.5 meters. And therefore, our kinetic energy is equal to 9 joules. Now from that information, of course, we know kinetic energy is equal to 1/2 mv squared. So now we can find the velocity at that point. So we get 1/2 mv squared equals 9 joules. Mass, of course, was that 2 kilograms times v squared equals 9 joules. Again, 1/2 times 2 is just 1. Square root of both sides, we get that the velocity is equal to 3 meters per second. All right, so for part B, it says, where is the particle's turning point located? So we can see that this is our turning point right here, but look, it's not like an easy answer. So we're going to have to use a different approach to find our turning point. So what we're going to do is we're going to use like triangles. So if I draw a bigger picture of my graph, I have a line that looks something like this, right? It goes down and then down again. Now here I can see that I have a like triangle right here, okay? So right here is my 20, and this triangle right here is going to match up with the 16 joules, oh my goodness, 16 joules here. I had 7 joules here, and then I can see my 20 lines up with 1 meter here. So that's 1 meter there. And then 16, this is what I'm trying to find, this X right here, where that is. And then this bottom portion lines up with 4 meters here. So my like triangles are going to be this big triangle right here, right, which has 20 at the top, 20 joules, 7 joules right there. So this big triangle right here, and then we're matching up with a smaller triangle right here. So we're going to use like triangles here. So the way we're going to do this is I have, I'm going to use my 20 minus 7 to get this length right here. All right, so 20 minus 7 over, and then the bottom right here is going to be 4 minus 1. And then I'm going to match this up with 16 minus 7, because I know that that's going to be equivalent to the 20 minus 7. And then my bottom here, we can see, is going to be 4 minus x. All right, so now we can solve for what x is. So 20 minus 7, that is what, 13 over 3. 16 minus 7 is 9 over 4 minus x. And then now we can cross multiply. So we get 13 times 4 minus x equals 9 times 3 is 27. Distribute this, so we get 13 times 4 is equal to 52. So we get 52 minus 13x equals 27. And then I'm going to subtract 27 from both sides, also add 13x from both sides. So we get 52 minus 27 is 25 equals 13x. Divide both sides by 13. And we get that x is equal to 1.923. So our x position, which is where our turning point is located, is 1.92 meters. So for part C now, it says evaluate the force acting on the particle when it is in the region 1.9 meters to 4 meters. So we can see that they kind of gave us the answer for part B and part C, because it says from 1.5 meters, which is our turning point. So remember, when we're talking about a force here, when we have a potential energy graph like this, force is going to be the negative slope. So what we want to do here is we want to look at the slope from this 1.9 meters, which is here, to 4 meters here. So the slope is going to be here. Now we can see that the slope is our rise over run, and here, of course, the rise is negative. So we get 7 minus 16 for our rise, over run, which is 4 minus 1.9. So slope here is equal to a negative 4.3. And then we know that slope on a potential energy curve like this is negative force. So therefore, force is equal to a positive 4.3 newtons. And there's our answer.